What if I told you that within the next 40 years, NASA could photograph the surface of a planet around another star? Clearly enough to see continents, clearly enough to see weather systems, and clearly enough, potentially, to make out cities and other massive structures on its surface if any exist. That isn't a thought experiment. There's an actual mission in NASA's books, currently in Phase 3 development at the Jet Propulsion Laboratory, that proposes exactly this. And the earliest realistic launch is 2034, with the first images, if everything works, arriving in the 2060s. The strange part is that the telescope built to do this isn't enormous. It's roughly the size of a backyard amateur scope. The reason it works is that the telescope isn't really what's doing the magnification. The sun is. That sounds like nonsense at first, except it isn't. Einstein worked out 100 years ago that any object with enough mass can bend light passing near it. Galaxies do it, black holes do it, and the sun does it. We've measured it directly since 1919. A handful of physicists at NASA have spent the last 15 years figuring out how to use that effect, and what they found, if it actually works, would let us look at planets around other stars more clearly than anyone has ever thought possible. This is how. Gravity, it turns out, doesn't only pull objects together, it bends light. Einstein predicted this in 1915, and it was proven during the 1919 solar eclipse, when astronomers measured the apparent positions of stars near the sun's edge and found them slightly shifted. The stars hadn't moved. Their light, on its way past the sun, had been pulled inward by the sun's gravity. That same effect is happening every second. Light from distant stars grazing the sun gets bent by its mass. Most of it bends a tiny amount and keeps going, but the light passing at exactly the right angle gets bent enough to come back together, to focus, at a specific region of space behind the sun. That focal region begins at about 547 times Earth's distance from the sun. To put that in perspective, Pluto sits at around 40 times that distance, and Voyager 1, after nearly 50 years in space, has reached 167. So the sun's focal region is more than 3 times further out than Voyager has gone. If you can get a telescope to that region, something extraordinary happens. The light from any star directly behind the sun gets amplified by a factor of roughly 100 billion, with angular resolution finer than any telescope humans could realistically build. To match what the sun gives you, you'd need a conventional space telescope with a mirror about 80 kilometers wide. Not 80 meters, 80 kilometers. That's larger than the diameter of Greater Los Angeles. And for comparison, the most powerful optical telescope currently being built, the extremely large telescope in Chile, has a 39-meter mirror, which means the sun, used as a lens, gives you more than 2,000 times its resolution. But there's a catch. This telescope cannot be pointed. The sun's lens has a fixed geometry, or for any given target star, the focal region sits on the exact straight line running from that star, through the sun, and out the other side. To image a planet around a different star, you have to physically move your probe to a different patch of space, possibly years of travel away. There's no aiming and no swiveling, because the telescope is the geometry of the solar system itself. And the image doesn't appear all at once either. The sun smears the planet's light into a thin ring around its disk, and the probe has to slowly traverse the focal region, sampling pixel by pixel over months, while a computer reconstructs the surface from thousands of measurements. NASA's Jet Propulsion Laboratory has been developing this for 15 years. The lead scientist, Slava Turishev, took the Solar Gravitational Lens proposal through 3 rounds of NASA's Innovative Advanced Concepts program, making it one of only 3 projects in NIAC history to reach Phase 3 funding. The current plan uses multiple small spacecraft, each under 100 kilograms, propelled by large solar sails. The probes first dive close to the sun for a gravitational slingshot, then unfurl and accelerate outward at 3 to 4 times Voyager's pace, which means the trip takes about 25 to 30 years. Each probe carries a 1-meter telescope plus a coronagraph, a device that physically blocks the sun's disk, so the much fainter ring of bent starlight can actually be seen. The earliest realistic launch is 2034, with first images arriving in the 2060s, and a demonstration spacecraft called Sundiver is already in development for a possible launch as early as 2027. Which brings us to the obvious question. Where do we point this first? Resolution improves the closer the target is. At maximum range, around 100 light-years out, the telescope produces a surface resolution of about 25 kilometers per pixel, which is fine enough to identify continents, oceans, polar caps, and weather on an Earth-sized planet. For closer targets, it gets dramatically better. The closest star to our own is Proxima Centauri, just 4.24 light-years away, the nearest of the 3 stars in the Alpha Centauri system. That's 23 times closer than the upper end of the SGL's range, which means a resolution of around 1 kilometer per pixel, or better. Mountain ranges, rivers, lakes, coastlines, and anything on the surface that doesn't look like geology. Proxima Centauri has 2 confirmed planets, and the most important one for this mission is Proxima b, discovered in 2016, roughly Earth-sized, and orbiting within the habitable zone where liquid water could potentially exist on a surface. Whether it has an atmosphere is still unknown. Whether it has anything else, we have no idea. If a civilization existed on Proxima b and had built anything large enough to be seen at kilometer-scale resolution, the Solar Gravitational Lens telescope could see it. A megacity covering a few thousand square kilometers would appear as a distinct geometric patch of color and texture, totally unlike anything natural geology produces, and the same would be true of large-scale agricultural grids, artificial coastlines, or any massive engineered structure. We wouldn't see individual buildings or streets, but we would see the footprint, the way a civilization shapes the surface of the planet it lives on. Artificial lighting on the night side, if it existed, would be a bonus. Another fingerprint. But the primary signature this telescope is built to detect is physical, structures, patterns, geometry, the kind of large-scale order that doesn't occur in nature, if anyone is there, if they've built anything that big. Neither is guaranteed, but for the first time in human history, both questions become testable. The Solar Gravitational Lens telescope is the only mission concept in human history with a realistic chance of photographing the surface of a planet around another star. And it does so using Einstein's century-old physics, a sun-sized lens that already exists, and a probe smaller than a car. Launch potentially within the decade, and answers potentially within our lifetime. If this is the kind of content you came here for, subscribe and stick around. Drop a comment. If the first image came back showing the unmistakable footprint of a city on Proxima b, what would you do with that information? That's all I have for today. See you in the next one.